Welcome to this new video. So now we are going to go through this question 7 in the May 22 time zone 2 paper 2. So we are told that we have a metal sphere positively charged and far away from other charged objects, and we know that the potential at the surface of the sphere is a 53.9 kilovolts. And so firstly we need to define what electrical potential is at a point. And well, this is just a definition that you kind of have to remember. Maybe remember seeing the formula in the data booklet, that the voltage is the work done per unit charge, might help you remember this definition, but there's just one of these common definitions that simply comes up too often for it not to be memorized. So it is the work done per unit charge that would be required, that would be needed to bring a small positive discharge from infinity to the point. So if we have some point here and we have a point charge infinitely far away, and this is just the work needed to bring it there divided by a charge of our point charge. So this is simply the definition of electric potential at a point. And then we are told that the electric potential at a point distance of 2.8 meters from the sphere, so let's say over here, not 28, only 2.8. Here it's going to be 7.71 kilovolts. We need to determine the radius of the sphere. Well, we can remember the other formula for the potential. This is the potential due to a sphere, to a charged sphere. It's just kq over r, like this. So from this, if we rearrange it a little bit, we'll see that VE times r is equal to k times q, where q is just a constant and q is the charge of our sphere. And we know that the charge of the sphere is constant. It doesn't matter where we are around the sphere. That doesn't in fact change the charge on the sphere or inside the sphere. So the potential times the distance is a constant value. And we know that at the surface, so the radius, so when we are at the surface, we only have the radius r. We know that that is going to be 53.9. So we know that 53.9 times this r will be, well, times the radius, so we don't know that yet. So just r, and this will be equal to 7.71 times the distance of that. And in fact, this 2.8 meters is from the center of the sphere, so we don't need to add the smaller again. We can just multiply by 2.8. And so from this we will find that the radius is 0.4 meters. And then part C, we are told that a small positively charged object moved towards the center of the sphere when it is 2.8 meters from the center of the sphere. So actually exactly at this point of potential we were talking about. It has a speed of 3.1 meters per second, and the mass of the object is 0.14 grams, and we're given the charge as well. And firstly, we need to comment on the angle at which the object meets the equipotential surfaces. And well, this is just going to be 90 degrees, as if we think about the charged sphere over here. We know that the particle is moving towards the center, so its velocity will be directed right through the center of our sphere. And we also know that equipotential surfaces are perpendicular to our field lines. So these will be like concentric circles around our sphere. And if I could draw it more nicely, we would see that this is a right angle over here. So it meets it at 90 degrees. And then we need to show that the kinetic energy is 0.7 millijoules. Well, we can just apply the formula, 1/2 mv squared. So 1/2 times the mass of 0.14 grams in kilograms, obviously, and we multiply by the speed, 3.1 squared. This will give us 0.7 millijoules, what we indeed had to show. And then we need to determine whether the object will reach the surface of the sphere. So what we can again think about are the energy conservations or the energy changes that take place. So there's our sphere, there's our little small charge. It's moving with a speed of 3.1 meters per second, and at the moment it's 2.8 meters away. So we know the potential here is 7.71. And we also know that if it would reach the surface of the sphere, it would be at a potential of 53.9. Yes, 53.9 kilovolts. So pretty much what would have to happen is that all of this kinetic energy would have to be converted into potential energy as it's becoming closer and closer. And when it reaches the surface, the speed would be 0. So the situation we would have here is that at the start we only have kinetic energy, and at the end we only have potential energy. Well, here we also have potential energy, but we can calculate this very nicely because we can see how much potential energy we need to reach the surface. So from knowing where it starts and where it ends up, we know how much potential energy it has to gain. And the only way it can gain this potential energy is by transferring its kinetic energy into it. So the E potential it must gain can be simply calculated from the formula. So the change in potential, the potential energy that it has to gain, will be the work done by the field, which is just Q times the change in potential. So the difference between the potential from the start to the end. And what we can calculate this is we know that the charge is 2.4 times 10 to the minus 8, if I remember correctly, yes. And then the change in potential will just be 53.9 minus 7.71. And so from this, we will find that the change in potential energy will be 1.1 millijoules. So this is how much potential energy it should gain. But we only have 0.7 millijoules of kinetic energy. So when we run out of kinetic energy, we will not be at the surface yet, as we would need a little bit more energy to make it all the way to the surface. So we need more energy to be able to convert all E kinetic to E potential. So since 0.7 is smaller than 1.1, we don't have enough energy to do that, and so we will not reach the surface. And so this is the end of question 7. I hope I was able to help, and see you in the next video.